So second third of AB Calculus. Start with a couple theorems that we have to know. First theorem is the intermediate value theorem. It's the first theorem we learned. Okay? F of x has to be continuous. For the intermediate value theorem to apply. The intermediate value theorem has nothing to do with derivatives. Typical graph will help you understand this theorem. We have some A and some B. We would consider this to be f of A and this to be f of B. If f of x is continuous, between f of A and f of B, there will be some x value that will produce all f of x's between f of A and f of B.
Did you say it a different way the first time that we learned that?
No, it's pretty much the same thing. Maybe I said it a little bit differently. Maybe I try and make it easier now. Who knows? Maybe it's harder now. Given this situation right here, can you guarantee that there is a zero somewhere? Yes, because f of A is below the x-axis, which means it's negative. F of B is positive. No matter how I draw this graph, since we're continuous, there will be some location, some x value, say the x value c, where f of c is 0. This was there exists. Backwards, uppercase E. Okay, so that's intermediate value theorem. It helps us ensure that there is a 0 somewhere. If I give you the points 2, -3, and the point 4, 5, you could tell me that if the function is continuous between those 2 points, somewhere between 2 and 4, there will be an x value that produces a y value of 0. Where? I don't know, but it's there. Okay? So something 0 will exist, and this has to be between 2 and 4. Great. Mean value theorem. You must be continuous and differentiable with the mean value theorem.
Why is differentiable?
I'll show you. This is extremely important. If in a question they give you a situation and they tell you you're continuous, but they don't specify you're differentiable, you cannot assume the mean value theorem applies. You must be both. Okay? Best is to draw a picture of 2 points, just like the last theorem. A, f of A, B, f of B. The theorem states that if f is continuous and differentiable, between f of A and f of B, there must exist some x comma f of x, some point whose tangent slope is equal to the slope between f of a and f of b. Okay, so the way we write that using some math notation is there has to be some f prime of x, that's the derivative, so that's the tangent slope, that's equal to the slope between f of b and f of a. We just use the slope formula to show that. So here is the slope of the line between A and B. No matter how I draw the connection between A and B, there will be some place, some point where the slope of the tangent at that point is equal to the slope between f of A and f of B. Doesn't matter how you do it. There must be one. There might be multiple. If I draw this a little bit differently and said we went up here and down here, well, we'll have two. We'll have this point up here who's got that tangent slope, that point down there who's got that tangent slope. Now, question is, why does it have to be differentiable? Because if I have a situation like this, sharp point, boom, there is no point whose tangent slope is equal to the slope between f of A and f of B. So a sharp point or cusp could make the mean value theorem not true. Therefore, you must be continuous and differentiable. A key question, and you'll see it in your homework, is they'll say the function is continuous, they'll set something up, and then they'll say there isn't a point that exists. Why? It's because the function's probably not differentiable. That's a key thing. Rolle's theorem is kind of a corollary to the mean value theorem, or vice versa. I'm not sure which one came first. Rolle's theorem, f of A is equal to f of B. And this theorem states that there must be what? A point whose tangent is what? 0. Yeah. No matter how I connect this, if f of A equals f of B, there must be some x. Which are not really x, it's a point. There must be some points between f of A and f of B such that f prime at that value is 0. So connect f of A and f of B however you want. There is some point where the derivative is 0. Has to be continuous and differential as well, just like the mean value theorem. Okay. Horizontal and vertical tangents. A horizontal tangent is when your slope is equal to what? Exactly. Vertical tangent is when what? Your slope is undefined. You will never see vertical tangents unless you have a non-function, which is like a circle or some curve that overlaps each other if you look up and down. So typically when you have that, you have an implicit equation. And when you take the derivative, you get some implicit derivative, like this. You want to find the horizontal tangents, you set the numerator equal to the 0. You want to find your vertical tangents, you set your denominator equal to the 0.
Of the derivative, correct?
Of the derivative, yes. Because the derivative gives you the slopes, and that's what you're looking for. Okay, so horizontal tangent when x is equal to 2 in this situation, a vertical tangent when y is equal to -5. Function analysis. Getting into the fun stuff. Not only does f prime tell you the slope of the tangent of f, but f prime also tells you whether f is increasing or decreasing. So, and if f is increasing or decreasing. If f prime is positive, f is increasing at that point. If f prime is negative, f is decreasing. Which brings us to our critical values and how we find extrema. Critical values are when f prime equals 0 or when it's undefined. Relative extrema are our relative maxes and mins. All relative extrema will occur at critical values, but not every critical value produces an extrema.
Is that like the x cubed?
Yes. The derivative is 0 at 0, but it's not a max or min. All extrema occur at critical values. Not all critical values are extrema. Let's talk about relative maxes. What must you show occurs to safely say we have a relative max at a location? Exactly. The sign of f prime must go from positive to negative. And we did these number lines to kind of show that. Now, you're not going to be able to use these number lines as proof. You're going to have to draw that number line, do your work, and then in your explanation you said, we have a relative max at A because the slope or the first derivative goes from positive to negative at A. Because we're going from increasing to decreasing at A. So you can do this, but then you'd have to say this in your justification. Relative min is when the sign of f prime goes from negative to positive. And of course, A could be 0 or undefined. It could still be considered a relative max or min. The tangent slope does not have to be 0. And you can say there's a relative min at x equals b since f prime changes sign from negative to positive. F double prime tells us about the slope of f prime, but it also tells us about the concavity of f. If f double prime is positive, f is concave up. If f double prime is negative, f is concave down. F has inflection points, or an inflection point, when f double prime changes sign. Okay, you need to be comfortable with looking at graphs of f prime. Analyzing graphs of f prime. Let's do this. This is the graph of f prime. This point here is A. This point here is B. This point here is C. I can ask you, when does f have a max or min? Relative. Just at C. Because that's when f prime changes sign from positive to negative. And C, therefore, would be a max or a min. A max. I could ask you, when is f concave up? To look at the concavity of f, we look at when f double prime is positive. Well, that means when is the derivative of f prime positive, or when are the slopes of f prime positive between A to B? What we also can do is put together the sign of f prime and the sign of f double prime to sketch f. Remember this from back in the day. So we'd focus our attention around A, B, and C. f prime is positive or negative between negative infinity and a? Positive. The sign of f prime, the function values are all positive. Between a and b, it's positive. Between b and c, it's positive. From c on, there it's negative. F double prime, negative or positive between negative infinity and a? Negative, and then positive, and then negative, negative. Now remember, this means we are increasing concave down. Increasing concave down. Increasing concave up. Increasing concave down again. Decreasing concave down. How do I sketch that? You just have your concave up piece, your concave down piece. You split it in half. You got your decreasing concave up, increasing concave up. Split this in half. You got your increasing concave down, decreasing concave down. You can now kind of sketch by combining the pieces what f is going to look like. Something like that. Where this is A, this is B, and that's C. Now, you might be asked, where are the absolute extrema? In this situation, you would be given endpoints or closed interval. You must be given a closed interval. So you're trying to find the max from A to B. So find the max function value, velocity, acceleration, whatever, between A and B. What do you have to do? Yes, find all the relative ones first. So sometimes it's not as easy as just sketching f. We don't have enough time to sketch it and test points. Instead, find the relative maxes. So find when f prime is equal to 0 or undefined. Test those values, and you must test the endpoints. For example, here is a piece of a function. From A to B. The min would be located where we have a tangent that's 0. That would be the absolute min. However, the max would be at the endpoint. Given that function on that interval. Straight line motion or speed. We need to talk about speed as well. But remember, we're given a position function. If I take the derivative of that position function, what do I get? I get my velocity function. If I took the derivative of my velocity function, I get my acceleration function. The absolute value of velocity is speed. So speed is always positive. If we're asked when is speed increasing, that's when your velocity and your acceleration have the same sign. If I'm going in the positive direction and I'm accelerating in the positive direction, I'm speeding up. the same if I'm going in the negative direction to the left. If I have a negative acceleration, I'm speeding up to the left. Okay, if speed is decreasing, opposite signs.
Was it test my class?
That's algebra. 2 classes we're taking a practice test, yeah. Okay, optimization. If you want to find the max anything, or the min anything, the max change in something, the max something, whatever it is, the min change in something, the min something, whatever it is, you just take the derivative, set it equal to 0. At those locations will be maxes and mins. If you're given a velocity function, and you're asked, when is your acceleration at a max? Or min, I don't know, whatever. You have to get your acceleration function, and then you take the derivative of your acceleration function and set it equal to 0. Because that will tell us when we have a max or a min acceleration. Velocity, acceleration, min. At that location, there will be a minimum.
Is it a minimum because it's negative?
It's a minimum because acceleration is like that. And this point right here would be a minimum. Where's that location at negative 10.6? Is it a good example because t is negative? No. It's just a minimum because acceleration is a quadratic that's opening it up, producing a minimum. Okay, but that's how you find, that's optimization, finding a max or a min. It's just taking the derivative of whatever you have, setting it equal to 0. Finally, related rates. Write down your info. d dt, whatever your formula is, that will produce what you need to find. Typically, it's like a volume. It could be a distance formula. We'll start doing some problems like that, reminding you of the problems that you've already done. And then you plug in your information and boom, you just solve. It's that simple, but it's usually not that simple. Anyways, great, that's it. That's part 2/3 of 3/3.